So we continue our journey through different types of work. So this time we're going to be dealing with spring work. And before you say, I don't deal with springs that often, well, you do more than you think, but there's a reason we talk about springs, okay? I promise that it has a very good use. Okay, so in this case, it's really easy to figure out like the force and the distance because it's simply, I have a force I'm applying, the spring stretches some amount. Great, I have it, that's good. Force times distance, right? Well, it's a little bit harder than that. Notice I have the dx here, and I also have that lowercase delta there. Why do you think I do that? Well, the reason I do that is because every infinitely small amount that I stretch that spring increases the force that it takes to do so. So if I'm stretching a spring from here to here, to begin with, it might take forces, let's just say 5. Then I'll take forces equal to 6 to go a bit further, and then force equals 7. You can see that the force actually changes with distance. So this is a bit more complex than you might think. So I will have to actually integrate that force to figure out what it is. Now, luckily for us, the force of a spring actually has a known equation. So K is a spring constant, and X right here, X is the difference from where it's nice and happy, where it's at rest right here, to where it is right now. So how far have you taken it from that point? Now if I integrate that using your skills you hopefully got from calculus, we get 1/2 K times the final distance from rest position squared minus the initial position from rest squared. So how far do you displace it for both of those? And we get our answer. And here's where most people start bothering me to say, well, why in the world are we talking about springs? We don't deal with springs that often. Get me there, okay? We're almost there. You deal with springs every single day and you just don't realize it. Every single moment. Okay, but before that, one last little example. This is simply showing that if I am going twice the distance, the force it takes to do that doubles. Okay, the force it takes to go twice the distance doubles, and the amount of work it takes is going to increase quite a bit as well. Now, here is where you deal with all those springs. You're like, but this is a solid bar, it's not a spring. Yes and no. Now, look at this equation right here. Work elastic is equal to integral of f dx. Wait a minute. That looks a lot like that previous spring equation. It does. It totally does. I could even make it look more like the equation, but I'm not going to do that quite. Well, I could. The analogy here is that force is equal to kx for spring, and stress is equal to the modular elasticity times the strain for a material. So these, one's called the spring constant, one's called the stiffness. Guess what? The stronger your spring is, the more stiff it is, the less likely it wants to. So you can see that these have very similar forms. We have something that's analogous to how much it's moving, something that's like a force, and then we have something that is all about how stiff and hard it is to stretch it. How much force do you have to apply to get it going? So in this case, this is where I'm saying you deal with springs every day, because everything, in a way, acts like a spring. If I take any material and I'm trying to squish it, now I might not be able to see it. Like if I'm just pressing on my table right here, okay? I have my table, beautiful table, glorious. And let's just say I put a book on it, okay? I got a little book there. Well, that is causing a force to be applied to that table. Now, I don't see the table move at all. The table looks like it's not moving at all. But if I were to look at it microscopically, what I would see, if I exaggerate it, is that it is bending underneath the force of that book. It's not much, but it is bending a little bit underneath the force of that book. So it's compressing like a spring. And the stiffer material is, the less it will compress for the same given force. That's why steel compresses a whole lot less than rubber does. Okay, so the last type of mechanical work we're going to deal with before we get another example problem, actually 2 in a row, is the work done to accelerate a body. Okay, so if I'm trying to accelerate or raise a body, let's go with raise for this first point. If I'm trying to raise a body, then the work I need is equal to the change in potential energy. If I'm trying to accelerate a body, then the work I need is equal to the change in kinetic energy. We already have equations for potential energy and kinetic energy, so this actually makes it pretty easy on me. And so elevators are great examples of this because they need both. First, it needs work to accelerate this and give this elevator car a kinetic energy so it can actually be moving. Once it reaches steady state, then it still needs work because it has to change the potential energy. Both of those are required to do this. Okay, so with that in mind, we're going to jump right into an example dealing with all the terms we've done so far. But I'll do that next time. Thank you all so much. See you in a minute as we do another example. Have a good one.